Welcome back. We will be continuing our discussion on deformation of a fluid element. So, just to recap what we have been looking at is we said if there are two adjacent points in a fluid x and x plus dx, and you know the velocity at the point x as u of x comma t, and the velocity at that adjacent point would naturally be u at x plus dx comma t. So, the question we started out asking is what would be the change in velocity or the difference in velocity between these 2 points. Between 2 points in space infinitesimally separated. So, we are using dx at the same instant in time. So, at a particular instant in time, we would want to find out that what is the difference in the velocity. So, if I write out my du would be u x plus dx comma t minus u x comma t. So, this is our approach to find out what is the deformation that a fluid experiences. So, for understanding deformation, we need to understand what is the difference in velocity between 2 points in space. So, if we now go ahead and exploit the fact that dx is small, we can do a Taylor series expansion for the velocity u evaluated at the point x plus dx about the point x. So, this would be u at x plus dx dot del u at x comma t minus u x comma t, and the terms that we are ignoring, they are in magnitude quadratic in the separation or higher. So, this is nothing but a Taylor series expansion, but obviously done in a multivariable sense. So, this particular object that we have, this is where we will start seeing how we are using tensors. So, if we write this in index notation, duy would become dxj dou ui dou xj. So, as dx goes to 0, the change in the velocity is related to the change in position via this object, which is known as the velocity gradient. So, this is the first foray that we have into studying something where we are looking at gradients of velocity. We have studied objects that are basically moving under the action of some velocity. The velocity could be unsteady, but this is an understanding of the non-uniformity spatially of the velocity field. So, this is the first time we are encountering this object. So, as I have said earlier that this quantity duy dxj, which is my velocity gradient, this is an order 2 tensor. So, because this is an order 2 tensor, I can do the decomposition, which is writing this as a sum of a symmetric and anti-symmetric tensor. So, this in general we can do for any order 2 tensor. So, I have done this split where the first part, as you can see, is symmetric about indices I and j, and the second part is anti-symmetric about the indices I and j. If you switch I and j, the first part preserves its sign, whereas the second part flips a sign, it becomes negative. So now why are we doing this? Why do we need the velocity gradient to be decomposed in this particular manner? Why can't we just say that given the velocity gradient at a particular point, I know that how does the velocity change in that neighborhood? Isn't that sufficient? Now the reason of this decomposition is to actually get a feel for what is the velocity gradient actually doing. Because the velocity gradient, as we have seen earlier, is going to be, if you think in terms of matrices, will have 9 elements. So it's not obvious how do we interpret those 9 elements. What do we make sense of those 9 elements? So rather by doing this split where the symmetric part is what I'll call as the rate of strain tensor. So Eij is the rate of strain tensor, that's the part that is symmetric, and the antisymmetric part is the rotation tensor. Which means that the velocity change that we observed, the velocity change can be split in terms of a symmetric contribution and an antisymmetric contribution, where the symmetric contribution is Eij Rj and the antisymmetric contribution is capital Rij Rj. So we have done this decomposition where we are trying to understand that if there are 2 points which are infinitesimally separated by a distance dx, they are going to have different velocities. So one would have u and the other would have u plus du if dx was small. This change in the velocity, so if the velocity vector was like this, here the velocity vector would slightly disagree. So this disagreement or difference in the velocity between 2 adjoining points has 2 components, and it is important to understand them separately rather than trying to say that I have a velocity gradient and thus I know what the velocity differences are. So let's first pick up the symmetric part. So we'll first consider the symmetric contribution of the velocity gradient, which is this object Eij. So we have the symmetric part of the change in velocity is going to be Eij Rj. Now this I will now apply or exploit a fact that I have this velocity change written in terms of a displacement Rj. So it is in terms of some change that you have in position Rj, and this will then be expressed. So let me just make sure I'm using my notations correctly. So Rj that I'm using here, this is just the separation of the 2 points. So this is dx that I'm using. So that's the separation that I have between 2 neighboring points. R is considered to be very small. So now this I can write as a gradient. I'm using index, so gradient of a scalar. Now I'll show this obviously by substitution. So if you take this scalar, which is half Rk RL EKL, you take a gradient of this quantity. So dou phi, it has to be a different index, dou Ri. Going to write this now as dou Ri Rk RL EKL. Now EKL is a constant. This object is a constant. We are doing a Taylor series expansion. So just to remind you, the velocity gradient when we are trying to find between 2 adjacent points which are separated by a small distance, the velocity gradient is related or evaluated at the, so when we calculated the velocity gradient was evaluated about the point about which we are expanding. Okay. So, here in this sense, when we are trying to find out a relation between two points which are very close by, the velocity gradient is not a function of space. The velocity gradient is a constant here, because every information that is being done here is in the neighborhood of 2 points which are sufficiently close to each other. So, that linearization gives us quantities like velocity gradients that are constants in that region. Once you understand what is going on with velocity gradient being constant locally, you can start to understand when in the broader problem when velocity gradient is varying. So, if I pull out that EKL, I have dou dou Ri, Rk, Rl. Now, this I use the product rule. So, I have Rl dou Rk dou Ri, Rk dou Rl dou Ri. Now, what is this quantity? Dou Rk dou Ri. So, for example, if you choose two indices here, dou R2 by dou R1, that would be 0. These are the three components of that small separation vector and they are orthogonal to each other. So, which is why dou R2 dou R1 will be 0, dou R3 dou R2 will be 0. However, dou R3 would be 1, dou R1 will be 1 and same would be applicable, would be 1 and the same would be applicable for dou R2, which means dou Rk dou Ri is going to be delta Ki. It is a Kronecker delta. You have these 2 points separated by this vector which is R that has 3 components R1, R2, R3. And now if you ask that how do each of these components vary with respect to the other components, they are orthogonal, which means that they will be independent of each other and then only vary with respect to themselves. So, that is in brief, that is what I have written here. So, similarly, the other one dou RL dou Ri is going to become delta IL. So, we will now write this. So, dou phi dou Ri is EKL RL delta Ki plus Rk delta Li. Now, let us apply this. We know that how the Kronecker delta works. So, whenever Kronecker delta is multiplied with something, it is like taking a dot product, that index gets replaced, which means EKL delta Ki is going to become EIL. So, the first term becomes EIL. For the second term, it is EKL delta Li. So, this becomes EKI. So, the index with which it is contracting, that index gets replaced by the other pair in the Kronecker delta. So, whenever you are doing a dot product or a contraction of a second order tensor or a third order tensor or a vector with the Kronecker delta, what the Kronecker delta does, it takes the repeated index, which is basically the one that is indicating the contraction, and swaps it with the corresponding free index. It is basically a multiplication with an identity tensor, because you end up getting the same object. It is an identity tensor. So, you have not done anything very fancy here. You have just formally written down in tensor language what is multiplication with an identity tensor. If you go back and think in terms of what a matrix does, this is exactly, if you have an identity matrix, this is exactly what it is doing. So, you are just writing this in a more formal sense in languages of tensors, because you are going to encounter objects that are not necessarily just a 3 cross 3 matrix or a 4 cross 4 matrix. You will encounter order 3 tensors which are not necessarily being going to be written in a matrix form. So, Rk is going to be Eki. Now, if you look at these two objects, one of them is actually in bold notation is E dot R, right? EIL into RL. The contraction is with the outer index of E. So, it is E dot R. Now, here this is R dot E, because the contraction is with the inner one. Now, this seems a bit now confusing, that the objective of doing all of this was to simplify what we had. Instead, now my original point was that DUIS is EIJRJ, and then by trying to convince you that this is actually the gradient of some scalar, I have landed here. Now, you see that E has a property. The rate of strain tensor is symmetric. That is the premise with which we started off, which means EIL is the same as ELI, which means for a symmetric tensor, E dot R is going to be the same as doing a R dot E, or EIL RL is going to be the same as ELI RL. So, that says that this particular term, which was RK EKI, I can write it now as EIK. So, what that does is that both the terms are now the same. L is a dummy index in the first term, K is a dummy index in the second term. Nothing particularly sacred about K and L. So, both are exactly the same. So, you get half into 2 RL EIL. So, that is equal to RL EIL. So, what we have written here is that the change in the velocity for the symmetric part can be written as a gradient of a scalar, because this object is a scalar. Sorry, this should have been EKL. Phi is that scalar. Now, it is still not clear what this achieves. We have just used the mathematical property of the rate of strain tensor being symmetric and managed to write that the change in velocity can be written as gradient of some scalar function because the rate of strain tensor is symmetric. That is just a mathematical statement. There is still no physical intuition regarding why this is being done and what this would actually give us. So, when you are writing something as a gradient of a scalar, what are you actually trying to do? So, that scalar that you have here, RKRL EKL. Now, this, as I said, EKL here for what we are trying to do is a constant order 2 tensor. So, this object is a quadratic function. RKRL, they will have indices. So, this will have terms like R1, R2, E12. It will have terms like R3 square, E33. It will have all kinds of terms like this. So, what this represents is a surface of quadratics. You have a surface in space that is basically given by this quadratic function. So, you have some kind of a surface that you can imagine being drawn like this, which is given by this scalar function. And the symmetric part, which is DUIS of that velocity, is given by the gradient of that surface. Now, gradient of a surface is going to point normal to that surface at every point. So, the symmetric part is actually a vector that is jutting out in the normal direction to that particular surface. Now, this gets easier if instead of choosing R in some arbitrary sense, like instead of having R defined in some arbitrary sense, we are going to choose a coordinate system R1 prime, R2 prime, R3 prime that is along the principal axis of Eij. Eij is an order 2 symmetric tensor. So, if you think in terms of its eigenvectors and eigenvalues, you can align yourself along the principal axis of that particular order 2 tensor, or if you go back to matrices, what that will do is that Eij in that transformed coordinate system, going back to how we learned tensors in the beginning, is going to become so if you align yourself along the principal axis, the order 2 tensor will become diagonal, right? If you remember the transformation rule, the transformation rule was the following, where C was the rotation. Now, how much rotation do you do? So, here you are rotating such that your axis is now aligned with the principal axis. So, when you do this exercise, your rate of strain tensor becomes purely diagonal. How does that help? Again, that could be a question, like why are we again moving along this? So, we will almost there now. So, what we said is dou u I s, the symmetric part, is the gradient of that scalar, which is dou Ri half R k R L E k L in the original coordinate system. Now, this now becomes, when you are doing this in the rotated coordinate system, in the rotated coordinate system, if I am trying to actually compute what this would be, so phi now turns out to be half, because if you remember, E k L prime only has diagonal elements. This is a purely diagonal quantity. Everything else is 0, which means the scalar doesn't change. You have to remember this. Scalar is not going to change whether you are doing in whatever coordinate system you do. So, the scalar, which was earlier Rk, Rl, Ekl, is now going to become Rk prime, Rl prime, Ekl prime, and this turns out to be half E11 prime R1 square, E22 prime R2 square, E33 prime R3 square. It becomes a very specific kind of a quadratic. Now, this, if you were to plot it, would be a surface that is given by the magnitude of what your E11, E22 and E33 are. Now, if I am trying to calculate what would be my the symmetric contribution in this new coordinate system that I have, 1 prime, 2 prime, 3 prime. So, if I am calculating the symmetric part of this, I just have to take a gradient. So, if I take a gradient of this, if I write du1, the first component would be half E11 prime dou R1 of R1 square. Everything else will be 0, right? So, this is R1 prime. You should just, this is all now in the axis, principal axis of the rate of strain tensor. So, let's write this. So, this is E22 prime dou R1 of R2 square, E33 prime dou R1 of R3 square. Now, these are 0. I am taking derivative with respect to R1 prime and obviously the contribution from R2 and R3 would be 0, which means the symmetric part is going to be E11 prime, and doing this derivative once I get R1 prime. Similarly, you are going to get du2s as E22 prime R2 prime, du3 symmetric as E33 prime R3 prime. Now, this is an increment in the velocity, right? So, we said that if there is a, so the separation between the 2 points is given by r, in this case I am writing it as r prime. So, if I have a small change, that dus1, this is going to be dr1 dt. That small change in the velocity is related to how the separation is actually changing. Because the 2 points are not having the exact same velocity, which means that their separation is going to change. So, the separation vector, which is given by r1 in the one direction or r1 prime in the 1 prime direction, that is going to change in response to there being a velocity which is du1 prime. Similarly, this is going to be dr2 prime dt and this would be dr3 prime dt. So, now you have an equation here which tells us that the separation between 2 points is going to increase. And as you can see, this increase, given that if you know what are the values of E11 prime, E22 prime and E33 prime, the separation distances are going to grow exponentially fast or shrink exponentially fast. So, if you are going to solve this equation r1 prime of t, that would be r1 prime of 0 e to the power exponential E11 prime of t. So, based on the sign, the 2 points are getting exponentially pulled apart or they are getting compressed. So, if we draw a diagram to say now let us have our coordinate system which is 1 prime, 2 prime and 3 prime, and I am going to draw an initial volume which is differential in size. So, there is a point in between and then I am trying to study, imagine the second point to lie on the surface of this small sphere. Okay. So, I have this differential sphere. By differential I mean that the volume is very small. So, the dimension of this sphere scales with dr. So, I am choosing the second point to lie on the surface of this sphere. Now, every point on the surface of the sphere is going to move because the velocity at the origin and the velocity at any point on the surface of the sphere is not the same. How is it going to move? The equations we have already written down, that dr1 prime dt is E11 prime r1 prime, dr2 prime dt E22 prime r2 prime, dr3 prime dt is er3 prime r3 prime, which means this sphere is going to become an ellipsoid. So, if you are sticking along any of these axes, they are going to get either drawn out or they are going to get compressed. Now, they could all be drawn out, they all could be stretched or they all could be compressed. But the first thing that we are learning here is that when you consider the symmetric part of the velocity gradient, the rate of strain tensor, what it does, it basically leads to an isotropic expansion, contract, not isotropic, but it leads to an expansion and contraction. It is involved in that stretching and compression aspect. But this should also make you start ask a question that are the two volumes the same? So, if this was the volume initially and this is the volume that you get after some time, should they be equal or that is not guaranteed? So, to do this, what we will try to actually look into is that we have this small volume. So, the question is that due to the symmetric part of the velocity gradient, should the volume of a differential element change? That is what we are asking. So, if I state this for an arbitrary sense, so I'll construct some box which initially at an initial time had dimensions which were given by vector A. So, there was some coordinate that I have defined for that initial thing. Now, due to the flow, this is going to distort. The flow is going to deform. So, if you think of it as a cube or you think of it as a sphere, it is going to effectively distort. And as it distorts, it now has a new volume which is dV. And I am basically saying that if I were putting labels of these points, so initially if any point inside this volume was given a label A, now the points are given by a label X. So, they were located at some points coordinate A, now they are located at some coordinate point X, and I am trying to ask the question that how does it go from A to X and how does that actually change my volume which was initially dV naught and dV. So, if I do that, if I write my dV, now dV for this new volume will be related via what is known as the Jacobian, because you are transforming from one label of coordinates to another label of coordinates. So, if you move from, let us say, Cartesian to cylindrical coordinate system. So, in Cartesian coordinate system, you have dx1, dx2, dx3 as a volume element. This is not equal to dr, d theta, dz. We know this, we have used this. There is a r that will appear here, then it becomes an equality. Similarly, if you were to write this in spherical polar coordinate, dr, d theta, d phi is not equal to dx1, dx2, dx3. There is an additional r sin theta that comes in. And how does all of these come in? How does the r and r sin theta come in? They come in via this Jacobian quantity that you have, because you are doing transformation from one coordinate system to another coordinate system. So, here you can think of the earlier shape having a coordinate system that is given by A and the new deformed shape having a coordinate system that is given by X. Hypothetically, if you think of like a cube becomes a sphere. So, in the cube you were using a Cartesian coordinate system, and then for the case of the deformed sphere you are now using a spherical polar coordinate system. So, that is essentially what is going on here. So, this is going to be the earlier volume, which is dA1, dA2, dA3, and dV is dx1, dx2, dx3. This is just a statement that how do volume elements transform due to change in coordinate system. Now this, which is the Jacobian for the transformation, can be written as the determinant of this particular matrix dx1 dA1, dx1 dA2, dx1 dA3, dx2 dA1, dx2 dA2, dx2 dA3, dx3 dA1, x3 A2, x3 A3, right. So now what we want to do is we want to find out that what is the change in the volume that I have, what is the rate of change of volume that I will primarily get. So to find the rate of change of volume, I am interested in calculating the quantity which is dJ dt, because dJ dt is going to tell me how much does the volume change. When I take a derivative, it will actually tell me that how much would the volume change in time. Because if J was not changing with time, the transformation of the Jacobian was not changing with time, then whatever was your initial volume would be the final volume. If J was a function of time, that means that your volume is effectively expanding, contracting, it's increasing, it's shrinking. So that's what you want to calculate. So when you try to calculate ddt of J, you have to basically take a derivative of this particular determinant, individual terms of the determinant. So that particular algebra I am going to right now just skip, because it requires taking the derivative of this determinant elements and calculating it. So when you do that calculation, dJ dt, where J is defined as this Jacobian transformation, will be dou u1 dou x1, dou u2 dou x2, dou u3 dou x3. This is coming in from the fact that J is defined in this particular way, because if you take a derivative of any of these elements, so just to illustrate one particular element, let's say you took the derivative of dou xi dou aj. So I will take the derivative, because finally the quantity that is changing with time is this new deformed coordinate. So I will take it inside. So I have dxi dt, which becomes dou ui dou aj, and dou ui dou aj I can write it as dou ui dou xk dou xk dou aj. So you can see that when I am taking a time derivative of any of these entries, it is going to be related to the velocity gradient multiplied by a similar entry. So ddt of one particular entry here is dou ui dou xj dou xk, sorry, dou ui dou xk dou xk dou aj. That is what is going to happen individually for those terms. So when you apply it individually for those terms, you are going to get the following relation. So we are almost there. So we have now a relation that ddt of the Jacobian is going to be the Jacobian times dou u1 dou x1 dou u2 dou x2 dou u3 dou x3. Now this in vector notation or boldface notation would be divergence of u. So if I take the j on the other side, I have ddt of ln j is divergence of u. And we have already said that the volume mapping dV is j dV naught. So, if there is an initial shape, the flow takes it somewhere else. By virtue of taking somewhere else, the shape also deforms. It's just not mere transportation of fluid matter. That region of fluid is also getting deformed. So, as it gets deformed, the change in that volume, everything now here is infinitesimal, is related via the Jacobian or the transformation that is happening. Now, that object is going to change with time depending on what is the divergence of u. And divergence of u, you can also now check has a connection to what we started out this section about, which was on the rate of strain tensor. The rate of strain tensor Eij is half dou ui dou xj plus dou uj dou xi. So, if you write this out, just the diagonal elements of the rate of strain tensor, that would be dou u1 dou x1 plus dou u1 dou x1 half of that. The next diagonal element would be half of dou u2 dou x2 dou u2 dou x2, and similarly the last one will also be dou u3 dou x3 dou u3 dou x3. So, the diagonal elements of Eij are dou u1 dou x1 dou u2 dou x2 dou u3 dou x3, which means this divergence of u is actually the trace of Eij, right. So, this brings us to an important conclusion. The rate of strain tensor is responsible for expansion of and contraction of material volume. If there are material elements that are there, those material elements under the action of the rate of strain tensor is going to get stretched or compressed. So, we are trying to basically break deformation into pieces. So, there is one part of the deformation which is responsible for stretching and compression, which is coming from this rate of strain tensor. Subsequently, the moment you start thinking of something being stretched and something being compressed, you will ask a question that would this exercise necessarily preserve volume? Just by saying something is getting stretched or compressed doesn't mean that I have told you anything about volume preservation. And you realize that volume preservation, if we have a further question about volume preservation gets tied to this particular quantity, the divergence of velocity, which is also the same as the trace of the rate of strain tensor. So, when divergence of velocity is 0 or the rate of strain tensor is traceless, Eij is traceless, they are the same. You should not say and or, but point is they are basically the same statement. When the velocity field is divergence free, in other words the rate of strain tensor is traceless, volume elements or material elements preserve volume for a divergence free velocity field. This is quite a different flavor in which how you have approached divergence free velocity fields. Typically, when we learn about divergence free or when we learn about what is incompressibility, it comes from mass conservation. Yes, we are going to bring in mass conservation, but whenever any field, here we are talking about velocity field, any field is divergence free, you can try to basically relate it in terms of some kind of change or alteration of a material element associated with that field. Now, for us, this is velocity field, which means what we are looking at is the volume. So, if you think of a volume And again, all these ideas are for material volumes is what I am giving. So when you think of a material volume means what? Like you define a region in space and then each point in space moves due to the velocity field. They are following a flow map. So they move due to the velocity field, which means they are going to occupy a different point in space in future. And that is to say that whatever was the initial shape enclosing those particles, that shape is not going to be preserved. That shape is going to become something else. So that is what the flow is doing. So when you look at the rate of strain tensor, the rate of strain tensor tells you how much would that material volume that you have, how much of it is going to actually get stretched and compressed. Whether it will get pulled apart, whether it is going to get compressed. So based on what you have here, if you now know that Eij is the rate of strain tensor, and if you do an eigenvalue eigenvector analysis of the rate of strain tensor, you are going to get the principal axis. And if along the principal axis, if the eigenvalue was to be positive, that means along that particular direction, the fluid elements are going to get stretched. If the eigenvalues were negative along a particular principal axis, that means fluid elements are going to get compressed. And if the flow is further divergence free, that means it has to preserve volume. That is to say, if it gets stretched along one particular direction, it has to be compensated by compression along the other direction. You cannot have E11. So what is not possible, obviously this is again like, an obvious statement, but if the flow is divergence free, E11, E22 and E33, all of them cannot be zero on all of them cannot be positive or negative. This is not possible. Because if all of them were positive or if all of them were negative, then automatically you violate the divergence free, or you are violating the fact that the volume is being preserved. Because if divergence of u is equal to 0, that means trace of Eij is 0, which means E11 plus E22 plus E33 is going to be equal to 0. That means you could write one in terms of the other two. So as you can see, if E11 and E22 were positive, E33 cannot take any arbitrary value. Its value gets fixed. So this is understanding of the kinematics, understanding of how deformation is occurring, and you are trying to actually split up how you think of deformation. So deformation, as you will see, what we will touch upon next is that we will touch upon the antisymmetric part or the rotation part. So today we went through the symmetric part to see that what the symmetric part does is it leads to this expansion and contraction. What the symmetric part also helps us understand is that if this expansion and contraction were to lead to volume basically being preserved, that imposes a constraint on the velocity field. And that constraint, as you can see, that constraint basically comes about as being that velocity field should be divergence free. So we'll stop here and then resume with the next part of the deformation, which is the rate of strain tensor's counterpart, that is the rotation tensor. So that is the antisymmetric part of the velocity gradient. So this is what we will pick up in the next lecture.